everybody, welcome back to Math 410. Sorry to get started so late. It's got a lot of stuff to write on the board and a computer to set up. Life is so stressful when you're teaching under these conditions. Anyways, plan for today is we're going to continue our discussion of symmetries of triangles and squares from class on Friday. And today we're actually going to get into what is the group structure that is created, because these S's and R's do in fact form a group. And if we have time then towards the end of class, we're going to start a new packet, which there are copies of I left at the door, which is going to be, we're going to start writing some elementary proofs about properties that all groups have in common, like that the identity element is unique for instance. I've got my usual office hours today from 2 to 3 in the afternoon, tomorrow from 10 to 11:30 and 1:30 to 2:30, and Wednesday in the hour before class and from 2 to 3. And as far as homework goes, homework 1 is posted on Blackboard. It will be due Friday night at 11:59 p.m. Questions?
To clarify, there are instructions as to how to sign up for office hours on Blackboard.
Yes, yes. As far as office hours go, if you go to the office hours tab on Blackboard, there is a link to a little doodle poll that where you can choose which hours you want to sign up for and sign up for a section. And there's also a link to how to access my Zoom, Zoom. So everything you should need to sign up for office hours is on Blackboard. If you have not yet, I recommend that in the very near future you try and download Tech if you plan on using Tech to write up your homeworks nicely. Or if you want to be one of those plebeians who uses like Microsoft Word to write up your homeworks, you are welcome to do that too, as a reminder. But I recommend you figure that out sooner rather than later so that because if 20 people, if I get like 20 emails on Friday evening at like 6 o'clock saying, I don't know how to download this, I'm just going to say, not my problem, and enjoy a nice relaxing dinner. But I will help, but I'm happy to help you. I definitely recommend that you get on that sooner rather than later. Any questions or any other questions or comments before we get started today? All right, let's do some math. So last time. Oh, the joke. How much do pirates pay for corn? I had to look over to make sure I'm recording. How much do pirates pay for corn? They pay a buccaneer. Okay, so last time, before we start splitting off into 20 conversations here. Last time we talked about how to find symmetries of the triangle. We said that that if you start with this 1, 2, 3 configuration, sorry, that table's a little bit in the way, but then there's 6 different ways that we can sort of rotate and reflect the triangle to get it to line up on with the same configuration it started with. If S is a 120 degree counterclockwise rotation, or if R is that, and if S is a reflection going straight down the middle like this, we found here are kind of the 6 different triangle configurations we could get. If we started here, a single reflection S will take us to here. A single 120 degree rotation will take us to here. R squared corresponds to doing 2 consecutive 120 degree counterclockwise rotations, which took us to there. RS, remember RS means do S first and then R. We have to read these from right to left, and today we'll talk about why we read these from right to left. RS or SR squared will take you to here. R squared S or SR will take you to there. And that's kind of the 6 configurations for the triangle that we found. So towards the end of class, at the end of class on Friday, I asked you to think about what are all the configurations or all the different symmetries of the square that we can find. So if this is our starting configuration, 1, 2, 3, 4 clockwise like this, what would be an example of a different square configuration we could get by reflecting and rotating? Yeah.
1, 4, 3, 2.
Like this?
Yeah.
Okay, how do you get to that?
So you just reflect it once.
1, 4, 2, 3. Yeah, if we do a single S, then 1 and 3 will stay in the same place, but 2 and 4 will flip-flop, and that'll take you to this configuration. How about another one? Right?
4, 1, 3, or 4, 1, 2, 3.
4, 1, 2, 3. How do you get to that?
3 rotations.
Ooh, going right for the R cubed, huh? Yes, if we rotate counterclockwise 90 degrees 3 times, or equivalently clockwise a single time, that'll take us to this configuration. So a couple others I'll just go ahead and draw up there would be R squared, which would be 3, 4, 1, 2. And a single R, which is 2, 3, 4, 1. Any others?
Which 2, 1, 4, 3. Rotate it once and then reflect it once.
So if you rotate and then reflect?
Yeah.
Okay, so that would be an SR, which is equal to R cubed S. Yes, that would give us another one. Okay.
You could do 3, 2, 1, 4, which would be R squared S.
R squared S, which I think would also be given to us by S squared, or no, S squared R, SR squared. Right?
And we go 4, 3, 2, 1. And you get that by rotating 3 times and then flipping, so SR cubed.
Yeah, SR cubed, or just a single RS should also get us the same thing. Any others? What about 2, 1, 3, 4?
It's not possible.
Not possible. Indeed. Yeah, it turns out these are all 8 of them. It's interesting though, because with the square, there are configurations of the corners, like there's ways to line up the corners that can't be reached from the initial square. The only way you can sort of do, you can't just flip-flop the top 2 corners without flip-flopping the bottom ones as well. You kind of have to tear off the top 2 corners and put them back into place, which is a big no-no, no tearing. Kindergarten rules. But it turns out that there are some ways that you can line up the corners for a square like this that you can't reach from rotating and reflecting. But with the triangles, you can find every possible configuration of the triangles. So we were able to find 6 configurations for the triangle, 8 configurations for the square. If we were to do this with the pentagon, any guesses as to how many we would get?
10.
What makes you say that?
Because it seems like it's double the amount of sides the thing has.
Indeed. Turns out that you can do this with, you can keep adding sides and do this as many times as you want. And in fact, the number of symmetries that you're going to find is going to always be twice the number of sides. So now that we have this, we can actually talk about what the group is. So the group structure that we're going to be making here is called the Dihedral Group. Now I'm on page, page 3. So here we have 6 symmetries for the triangle. We have 8 symmetries for the square. And for a regular n-gon, meaning a polygon where all the sides and angles are the same length, but with n sides to it, it's just going to be 2n. So, if we flip the page again, all these R's and S's, when we combine them together, are actually going to form a group of symmetries that's called the Dihedral Group. And the Dihedral Group, when I talk about symmetries, just so we're on the same page, the symmetries are not going to be these individual square corner configurations. The symmetries are actually going to be the reflections and the rotations in combination that it takes to get from this position to this position. So think about S, for instance, as not being this square by itself. S here is going to refer to this act of reflecting over this line. R is going to refer to a 90-degree counterclockwise rotation. And if we combine all these R's and S's that we can find together, that's going to give us the dihedral group. It's the group of symmetries in general of a regular n-gon, where n equals 3, a regular 3-gon is just a fancy way of saying equilateral triangle. If n equals 4, a regular 4-gon is a fancy way of saying a square. But regular n-gon in general is just a shape with n sides, all of which are the same length, and all of the angles are the same within the shape. So, for instance, if we wanted to write out the elements of D3 as a set, we're looking at the symmetries of the triangle. We're going to have R, we're going to have R squared, we're going to have S, we're going to have RS, we're going to have R squared S. What am I missing?
One, like R to the 0.
R to the 0. Or just R cubed would be another way of writing it. If you just something where I pick it up, rotate it in a full circle, so in effect it's the same as what it started, and put it back down. That would be the symmetry that starts with, say, this triangle and puts it back down in the exact same position. R to the 4th would do the same thing for, say, the square. So this is going to be kind of the elements in our group. Question, what about SR? I didn't write out SR in that set.
It'll be equal to one of the other.
Yeah, it's going to be equal to one of the others. In fact, SR is just going to be equal to R squared S in this group. And so we don't need to write it out separately because the effect of rotating once and then reflecting once is going to be the same as the net effect of reflecting once and then rotating twice. So technically you could rotate any integer number of times and say R to the 5,000. But R to the 5,000 is just going to be 5,001. R to the 5,000 is actually just going to be the same as R squared, it turns out. So there's lots of other ways you can combine R's and S's, but it's always going to give you something that's equal to something already listed in this set, one of these 6 elements. And then the group operation is we're just going to say that R star S, for instance, is just going to be this RS symmetry. Basically, if you combine 2 symmetries, like R and S under the group operation, you just kind of smush them together and see what symmetry you end up with. What would happen if I wanted to take a symmetry found by doing R squared S star RS? If this is a group, then we should be able to combine any 2 elements in the group and get back something in the group. But I don't see an R squared SRS listed anywhere in this set. So how could we actually do that multiplication, or do that composition? By the way, when I say R star S is just equal to RS, there's a fancy name for this. We're doing function composition. Yeah, Ron?
I think the 2 S's will cancel out.
Do they?
So, I think so.
I agree, they would if they were right next to each other. If we had an S squared.
Yeah.
The problem is, this is not a commutative operation. We can't say swap the SR and make that an RS here because RS and SR are not the same. What could we do? What could we do instead if we wanted to multiply these out? Kind of raised a single eyebrow. It's not working very well. Here.
Well, you have associativity.
Indeed.
You'd be able to switch out the r squared, or the SR, you'd be able to switch that out for r squared s. Which
Okay.
gives you r squared s.
Yeah, we can rely on the fact that we have associativity, meaning we can add parentheses wherever we want. So this SR here, we can swap out with an r squared s. And that keeps slipping on me.
You can continue with that, well, because then you can take the parentheses out, and then you would have s squared, which I'm reading from right to left, and then r to the fourth,
Yeah, we can actually replace this
which would just be
r to the fourth s squared. And now, Rowan, I think we can do what you had suggested earlier and say, if you just do s twice, reflect again, those will cancel out. This is going bye-bye. And then r to the fourth is the same as doing just a single r. Yeah, so it turns out r squared s times rs is going to give us something back in the group. You just have to do a little bit of associativity, playing around with things in order to find out which of these group elements it actually gives you. In fact, it's just a single rotation. By the way, here's the reason why, and this is a bit confusing, I think, when looking at the Dihedral group. The reason why we read, say, rs as do s first and then do r is because if you think about, if we were composing two functions, think about r and s as each being functions. R is, it's a function that takes in a square, and then what it spits back out is another, or a triangle, and then it spits back out another triangle that's been the same thing that's been rotated. R is a function that rotates a triangle. S is going to be a function that takes in a triangle and just does this reflection, or spitting back out the same triangle. If I were to write out to you log of x, if we're composing two functions, f composed with g, and applying it to some variable x, which one are we going to do first to x? Are we taking g of x and then plugging that into f of x, or are we going to take f of x and then plug that into g of x?
We do g of x first.
Yeah, you do the one that's closer to x first. So when you write out function composition like this, what you're really saying is do g, then f. So in essence, when we say r, something like, let's go over here. rs means do s first and then r. What you're really think of it this way, like rs is taking in a triangle, and it's doing s to it first. It's taking this triangle and reflecting it, and then it's rotating it. And so that's why we read out these symmetries from right to left when we're seeing what does it actually do to a triangle or to a square or to a regular n-gon in general. It's because function composition is sort of written out as do the rightmost one first and then work your way to the left. It's a little counterintuitive because I'm used to reading out rs as do r then s, but when you think about it as being like each of those as being a function, and the way you combine them is doing function composition, it sort of makes a little bit more sense to me, at least, why we would have to read it out from right to left in order to be able to say, do the one that's closest to the triangle first, and then work your way outwards from there, just like with f composed with g of x. It's a little confusing because when you do the group operation here to combine symmetries, you actually just write them all out from left to right still like this. Or this is technically saying, oh, if you want to compose the actions of reflect and rotate twice with the action of reflect and rotate, what you did is a single element, which is the same as reflect once, rotate once, reflect once, rotate twice. which is the same as just rotating a single time, as we've already seen. Any questions about any of that? Yeah, Rob?
What would the identity be?
Oh,
For cube?
what a good question. That was gonna be my next question. Yeah, we have a group. I said this is a group. If it's a group, it has to have an identity element. What is our identity element? The symmetry that takes in the triangle and will spit back out the exact same triangle.
That would just be the R cube.
Yeah, R cubed is actually going to be the identity element here, because that's the transformation that spits back out the exact same shape as we would throw into it.
Why would it be r cubed instead of s squared? Or is it both?
It's both. S squared would be another way to write the same thing. I just wrote I said R cubed because that's the way I happened to write it down here. But instead of R cubed, you could just put S squared if you prefer. And it's a different way of writing out the exact same transformation, in which the net effect is you take a triangle, you pick it up, and you put it right back down. If you want, you can reflect twice, or you can rotate 3 times, and either way, it'll end up, what you do in the middle doesn't matter. What matters is the net effect at the end. And in that sense, R cubed, S squared, and doing nothing all are going to be the exact same symmetry. These chalks are small. Dr. Murphy, thanks for giving me chalk. By the way, if we're looking at the D4, the dihedral group here, what would the identity element be?
R4.
Yeah, here it's going to be R to the 4th. It's going to be rotate 4 times. And R cubed is actually not going to be the identity element in this group. Because you rotate 3 times 120 degrees, well, that's 360 degrees. You've gone right back around. But if you rotate 90 degrees 3 times, that's not a full circle. That's just 270 degrees. So I have to be careful in that the identity element kind of takes different form depending on which dihedral group you're looking at. Usually when we write out the dihedral group, though, if we're talking about the identity transformation, we usually just write E. You can say R cubed or S squared or R to the 999th if you prefer. Or R cubed S squared would be another way to write it. But they're all different ways of referring to the same thing. And so usually it's just E is used to refer to, make it very clear, this is the identity element of this group. Any questions about any of this? One thing you can try for fun, that I encourage you to try in your own time, is to find inverses of all the elements. For some, it's not so bad. Like R inverse is R squared because R times R squared is the identity. For R squared, it's R for the same reason. S is its own inverse. It's going to turn out that RS and R squared, RS and R squared S are also going to be their own inverses, but it's a little harder to prove. You just have to do this sort of math to show that RS times RS is the identity, R squared S times R squared S is the identity. I say times when I really mean composed with, but oftentimes when you're talking about groups and you just want to talk about the group action, you just say times as sort of a sloppy way of saying, do the group action, whatever it is. So, let's have some fun now. You may have noticed if you've looked at homework 1, there's a few group candidates that I gave you that are actually given to you in table form. That actually has a specific name for a group called the Cayley Table of a group, which is basically, it's just like a multiplication table for the group. It's just a table that tells you if you multiply this group element by that group element, this is the thing that results. Let's actually take a minute and I want to see what happens if we find the Cayley table for D3. So for D3, the way this works is you start by writing out all the elements of your group kind of in a header on both like on top and to the left. R squared, S, RS, R squared S. And if you want to see what happens when you multiply two group elements together, the first element, you go to its kind of corresponding row. So if we wanted to see what happens when we do R times S, we would go to the row for R and the column for S, and what's going to result is just going to be RS. All right, let's see if Dr. Burstel can do this. First row and first column is always easy, because what's the identity element times anything in the top row? Yeah, just the same thing. So the identity element times anything here is just going to be the same thing. Ditto with the first column. Anything times the identity element is just going to be the same thing it started with. This will be R squared, S, RS, R squared S. R times R is going to be R squared. R times R squared is going to be the identity. R times RS is going to be R squared S. What's R times R squared S going to be? The R will combine with R squared to make an R cubed, which cancels out, and they'll just leave us with a single S. Let's see, this will be R squared times R will give us the identity. R squared times R squared will give us a single R. What's be a pirate, bonus joke, what's be a pirate's favorite letter?
You'd think it'd be R, but they love the C.
I, it'd be the C. Also I. Let's see, this will give us an R squared S, this will give us just an S, this will give us an RS. Oh, it gets fun when you start getting to the rows with the S's in them, because now you have to say, all right, what's S times R? R squared S, not going to be RS. S times R squared will give us an RS, S squared is the identity, S times RS is R squared SS, which is an R squared, and this will be an R. At this point, I'm going to give up and look at the table that I did ahead of time, so this doesn't take the rest of class, because these are going to get annoying. S, R squared S, R, E, R squared, RS, S, R squared, R, E. And there we have it. That is our Cayley table for D3, the Dihedral group on a triangle, the group of symmetries of a triangle. Tells you, if you have this table in front of you, then it's easy to multiply any two elements of the group together. You just go to the corresponding row and column, and boom, there you go. Does anybody notice anything interesting about the individual rows and columns of this table? So if we were to look at just the row for R squared, say, anybody notice anything about all the different elements that we can come up with? Here.
Every single, like, of the original one is in there.
Yeah, every single one is in there how many times?
Once, exactly.
Exactly once. Every group element appears in the row for R squared exactly once. And if you notice, the same is going to be true if we were to pick any row in this table or any column. Every single group element is always going to appear exactly once, which is kind of interesting to me. And in fact, no matter what group you're looking at, that's always going to happen. In any group, if you take the Cayley table for any group, every single group element is going to appear exactly once in each row and in each column. Each group element appears exactly once in each row and column. So if, for instance, you're working on homework 1 and you happen to see a table where that property doesn't hold, that should tell you something is going wrong and what you have is not a group. Hint, hint. Yes,
This makes me think of Sudoku. Is there any connection between Sudoku and group theory?
there is a lot of connection between Sudoku and group theory.
Cool.
But that's a big conversation to have right now. That might be something where if we have time towards the end of the semester, I'd love to spend a day just talking about that. Yeah. There's also a game called Set that I actually have a project for later in the semester, a card game that we're going to do like a whole homework assignment around.
Awesome.
Dr. Gerstle, why is it the case that every group element appears exactly once in each row and column? That's a very good question. So good a question that I'm putting it on homework too. So have fun with that next week. It turns out that the reason why has a lot to do with inverses of individual group elements. So I'll say for now. But this will be a question you're actually going to get to prove this on your homework for next week. Yes, Rowan.
Before we prove it in homework 2, can we use it for homework if need be and stuff?
Sure. Do you want to use it on homework 1, for instance? Yeah, you're welcome to use this on homework 1. However, for the things that are not groups, you had to say which of the 4 group properties are not satisfied. So you could certainly use it to help you determine something is not a group, but you then would need to go through and check which of the 4 properties is actually broken by this. But it's certainly something helpful that might tell you, for instance, that, I don't know, table number 3 does not correspond to a group on homework 1. And then it's up to you to find out why is it not a group? Which of the 4 properties is broken?
So also there's no dihedral group, it's a bunch of dihedral groups.
Correct.
Right.
When we talk about the dihedral group, technically we're talking about an entire class of groups in general, and if you want to specify which one, you have to say, let's talk about the group D3 or D4 or D100. Talking about groups or dots. Anyways, any questions about any of this? So the dihedral group is interesting in that it's kind of our first example of a finite group, meaning a group that doesn't have an infinite number of elements in it. The kind of 2 previous examples we've seen, like the integers under addition or GL2R under multiplication, those are both examples of infinite groups. Which, by the way, if you try and draw a Cayley table for an infinite group, that might take you a while. Like forever. So typically you only do Cayley tables for finite groups. Technically, this property right here does hold true for a Cayley table of an infinite group. You just have to account for the fact that your rows and columns are going to have infinitely many things in them. But this property will hold true for every group, including ones that are infinite.
Will there be situations where we can represent an infinite group with a finite type table? So I'm kind of thinking of how you can do stuff in modular arithmetic. Is there
Yes,
something
that'll be an example. Yes, that will be an example actually, Z mod NZ, that we're going to talk about in a week or 2.
Okay.
Of basically exactly how to do that. I'm going to introduce it as a finite group, and then later on in the semester, once we talk about quotient groups, we'll talk about how we start with something infinite, mod out by a relation, and we end up with something finite. Yeah, that's a good observation. And kind of the only time when you would try to do a Cayley table for something infinite is if you're looking at it in a finite way. If that makes no sense to you, it didn't make much sense to me either, and we'll make more sense of it together in a few weeks. So dihedral group is also interesting. Question, is this group commutative? Meaning, is AB always equal BA? Right? Prove it. Okay, give me a specific example of 2 elements that do not commute with each other.
RS and
There we go. R times S does not equal S times R, so this group does not have the commutative property. Technically, we have a fancy name for groups that have the commutative property. We call them abelian, after Eric Abel, who's a famous mathematician, group theorist. not a commutative group, since, for example, RS does not equal SR in this group. Have we seen any other groups so far that, well, let's talk about their two groups. Were the integers an abelian group? Integers are certainly abelian under addition. A plus B is equal to B plus A for any integers A and B. How about GL2R? Was that an abelian group under multiplication? If we have two invertible matrices A and B, must A times B be equal to B times A? That would be a negatory. So far we've seen an infinite abelian group, a infinite non-abelian group, a finite non-abelian group, and probably in a few classes from now we'll look at a finite abelian group. Okay, that's going to do it for this package. I introduced the Dihedral Group because it's kind of an interesting example that I think ties nicely into geometry. And it's kind of a nice and it's kind of our good first example, I think, to start with for an example of a group that is finite, that only has 6 or 8 or 2 in general elements to it. If you really want to have fun, think about how you would do a Dihedral group for a circle. Anyway, so that's going to be it for that packet. Because that would be an infinite group, actually. So next up, we're going to start this next packet, group property, where we're going to kind of talk about how you would actually write mathematical proofs for some of the things we've been talking about. Now this one is, because this is going to be a lot of what we're doing for the rest of the semester is saying, if we have a group in general, we don't know what type of group it is, but maybe if we have a just group in general, or if we have an abelian group, what must else be true? If, in this case, if we have any group at all, what are some of the properties that that group has to have that are not going to be clear immediately from the definition? So for instance, our first proof is going to be proving that groups can only have a single identity element. Right, I think you were asking me about this on the first day, like can a group have multiple identity elements? It's not immediately clear from the definition, but it turns out that the answer is no. There can only be one element in the group that if you multiply by it, do the group action multiplying on, or do the binary operation on it, nothing changes. That was a whopper of a sentence I just said. So here's going to be our first theory. Is that let G be a group. Then G must only have one identity element. So, first proof. I'm going to go slow. I'm going to try and go through these first couple proofs very slowly, just so everybody's kind of on the same page, because I know some of you have probably taken courses where you've had to prove things before, like analysis or my discrete math course, etc. Some of you, this might be your first proof course, in which case it's probably going to be a bit of a challenge to get started doing. But I'll try and go slowly, and feel free to stop me at any point if you have any questions. Okay, for those of you who've proven things before, I want to show something is unique, the identity element. How do you show something is unique? As a general proof strategy. Okay.
Assume that there are two of them and then show that they're equal to each other.
Bingo. So here's going to be our strategy here. To show that our identity element is unique, we're going to show that if there are two of these things, prove that they must be equal to each other. And then if any two of them must be equal, then they must all be equal to the same thing, and there can only be one. So here's how the proof's going to go. By which I mean, that's how every proof is going to go. like any good proof, should start with an introduction. It's going to have a body, the bulk of like actual proof, and then it's going to have a conclusion. Dr. Versatile, is this an English class? Yes, it is. But what I mean by this is the introduction is where you're going to establish what are the things you're working with. What are sort of the tools you're giving yourself? The conclusion is just going to be restating what you have proven. And the body of the proof is going to be where the actual proof writing goes, like where you actually show that conclusion follows from introduction. So let's actually start off by trying to do that here. So that's kind of an outline of how every, I think, good mathematical proof should go. Is you start by saying, here are the things I'm working with. Given these things I have to work with, I'm going to work with them in the body. And then the conclusion is going to be, here is what I have shown. So in this case, our conclusion is going to be, thus G can only have a single identity element. So to start off with, you need to give yourself the tools you need to actually be able to do anything. So we're going to start with, let G be a group. And Nick suggested we suppose we have two identity elements and show that they're the same. So we're going to let E and E prime both be identity elements of our group G. So in other words, we're going to assume that for any element A coming from your group G, E times A is going to be equal to A, which is A times E. And also that E prime times A is going to be equal to A is equal to A times E prime. That's going to be our introduction. When we write a proof that holds true for any group like this, we need to be able to prove things in as much generality as we can. By which I mean, we want to be able to write a proof that holds true whether our group is the integers, the GL2R, one of the dihedral groups. Doesn't matter. We want to be able to write our proofs that we could replace G in our proof with any group that we want, and the same argument would still hold true. So typically, you do that by at the start writing something like, let G be a group. Now we're going to work with an arbitrary group G that could represent anything. Just like in calculus, where when we do things with x's, we assume that x could represent any number. And then also, next suggestion, we're going to suppose that we have two different identity elements, E and E prime. And this is just what it means for E and E prime to be identity elements. Now, did anyone notice what I left out from this equation? Because I actually left something out as I wrote this. Right?
The little stars that need to be in function.
Yeah, the little stars. Technically, I should be saying something like E star A is equal to A is equal to A star E. And maybe I should have included those, but in general, when you write out a group, if it's understood what the group operation is, you just write out like EA, and then it's assumed that when you write something like EA or E prime A, that what you really mean by that is not necessarily multiplication per se, but it's just E star A, and we just leave out the star because it's a bit cumbersome. So from now on, when we talk about groups, we'll often not write out the star, just because EA is assumed to mean E group. E binary operation A. So if G is the general linear group, EA could mean matrix E times matrix A. Whereas if G is, say, the group of integers, EA really just means integer E plus integer A. And if it's a dihedral group, EA means identity rotation E composed with whatever symmetry A corresponds to. All of these are going to be the same thing, which we're just going to refer to without the star for the sake of convenience. So that's going to be our introduction. Nick, can you remind us what we would like to show about E and D prime?
We're trying to show that they're equal.
So here's going to be our conclusion. Thus, E equals E prime. And so we must have, and so we know G can only have one identity element. Introduction. This is our introduction in that we're not really proving anything yet. We're just saying, all right, suppose we have a group and we have two identity elements. We're kind of establishing here are the individual pieces that we're going to get to work with. In this case, the fact that we're working in a group G and the fact that we're working with two individual identity or two identity two identity elements. This is going to be our conclusion, where in our conclusion, we're just saying, hey, we've proven the thing we want to prove. And if you didn't remember, here's what we've actually proven, that G can only have a single identity element. And then the body of the proof is just going to be all the work that's necessary to go from these starting pieces to, in this case, showing that E is equal to E prime. Any questions about any of those individual pieces, the introduction or the conclusion? I think, especially if you're writing out proofs for the first time, it might be helpful to kind of start by just writing out what do you want your introduction to be and what do you want your conclusion to be. Usually those pieces are not as hard. Doing those two pieces is not as hard as writing out the bottom, where you actually have to find the logical connection between this stuff and that stuff. So now it's time for the body. And by now, I mean on Wednesday. So on Wednesday, we'll start by writing out the body of this proof, and then we'll go on to proving some more properties, including things like uniqueness of inverses, and also socks and shoes. We're going to prove the socks and shoes theorem on Wednesday. Yeah, it's a fun one. You know, and it's all about putting on, you know how to put on your socks and shoes? You're weird. Look on the class Wednesday.